Okay, welcome back everybody. We're ready to start off now with some more machine learning, and Hilde did a project together with Neptune on facies classification, how logs can be used together with machine learning for facies classification. So I'm really happy to have you here, Hilde, and feel free to kick off.
Thanks, Toffe. So yeah, my name is Hilde Tveit Haaland. I'm a geophysicist by background, and I currently work in Cegal as a senior geophysicist / data scientist. So for the last 4 or 5 years, I've been working kind of more towards data science than just purely geophysics. So yeah, as Toffe said, last year we did a project together with Neptune, who's a small, or yes, they're not too small. It's a Norwegian oil company that has a fair amount of North Sea assets, and we performed a project for them, basically, where we tried to use machine learning to predict or to classify facies from petrophysical logs. I can't. Yeah, sorry. So just a little bit of background. Neptune and Cegal had a collaboration project set up that was kind of larger than this this specific product that I'm going to present. So we kind of set up a digitalization group for Neptune, where we kind of worked and provided them resources within digitalization and innovation. And part of the purpose of that group that we had set up was to work with users at all levels in Neptune to try to discover and then mitigate pain points in their workflows. So I've written subsurface workflows here, but we actually also worked towards finance and yeah, other parts of the organization as well. So lithofacies was kind of identified as one of these pain points in their subsurface workflows when we were talking to geologists and geophysicists on their assets, and they described it as a time-consuming task. Sorry, where geologists would spend like a large amount of time trying to create consistent interpretations from well to well with differing petrophysical log content in the different wells, and this was kind of identified as a part of the process where they needed a higher turnaround to be able to feed models during drilling campaigns, for instance, so that they could quickly kind of utilize the data that they acquired when drilling new wells. So yeah, this kind of the project definition is kind of set up as a part of a specific use case for a field which had a couple of successful exploration wells, and they had a drilling campaign set up over the span of last year, where they would drill several more wells, and then they wanted to kind of minimize the time from drilling the wells to having data that could go into geomodels. So they wanted to kind of continuously update their models as they were drilling wells, so that they could then potentially identify the danger points, or optimize their well placements if needed. So to try to kind of achieve this lower turnaround time, it was decided to test a machine learning driven approach to lithofacies classification. So kind of instead of the geologist that we were kind of working with, instead of her spending the main bulk of her time trying to create the lithology logs manually when the new wells came in. We aimed to build an application or a piece of code for her that would allow her to spend a fair amount of time up front to build a classifier from one or two of kind of the good discovery wells that they had, which could then be applied to the future wells as they came in. So that would alleviate kind of the time-consuming part of the lithology interpretation, and then kind of free up the time that this geologist was using creating the interpretations to actually QCing the machine learning output. So instead of spending a lot of time on the manual labor, you would spend a lot of time on QCing outputs instead, which would hopefully then speed up the process. And then as a kind of side point or bonus, if you want to say, when using a classifier to predict your lithology in kind of the new incoming wells, you would then kind of mitigate the uncertainty for kind of biasing your interpretation. So if you have two geologists working together, or one geologist having a lot of time to do one interpretation and then she has to kind of speed through the other one, you might focus on different things when you do your interpretation. So by having a classifier do the interpretation for you, you kind of make sure that it's not biased by kind of human either error or human preference. So we needed to land a tech stack for this project. And as I guess Tom, who spoke before me, mentioned, we're mainly using Python in the data science part of Cegal. So it was kind of quickly decided that we would use Python, as that's where we have our expertise. So we decided on Python, with considering that we have fairly small sets of data when we're working with well logs. I mean, a well log has a lot of data points in it, especially if you kind of have a lot of logs. But considering it or compared to actual big data, a well log is quite small. So we ended up deciding to use scikit-learn, which is a fairly basic machine learning library that's open sourced, but it's kind of a golden oldie. It's reliable, basically, and good for smaller data sets. We also decided to use a classifier called XGBoost, and then we wanted to kind of make sure that we focused on evaluation of these machine learning algorithms as we went along. So we looked at different libraries that would allow us to kind of evaluate output and models used in machine learning, and we ended up on SHAP for that, for those who knows or are familiar with SHAP. And at the same time, we had to kind of think about who our end user would be. So I mentioned we were specifically talking to one geologist who was responsible for this field where they were having this drilling campaign. And she was initially quite interested in just having basically a piece of Python code that she could run in a notebook or in another Python environment. And then we could set up some kind of workflows that would alleviate, a bit of the coding pain for her, but that she would have a lot of flexibility when trying to build these classifiers that she would try to build. So that was actually kind of our first decision to deliver this this product as code. And as the project kind of progressed, both the user and us writing the program kind of saw the need for having an easier way to interact with the code. The code very quickly grew, and it got to be I was just going to say it would have been quite a steep starting point for someone trying to learn Python to just go in and directly use this code. So in the end, we actually ended up with delivery option 2, which was an app-based interface for this problem. So the app framework that we used was a web app framework called Streamlit, which is kind of a web app framework that's built for building machine learning apps. So it's a really nice tool for those who are interested in checking it out. So we basically wrote Python modules that we could run then in any interpreter, and launched a Streamlit web app from that. And the beauty about a web app is that I'll show you, I'll demo this web app in a few minutes here. And then I'll just host it locally on my computer. But with the code as it stands now, I can very easily also just serve it on a public cloud somewhere, or non-public cloud, whatever is easiest. So it's easily distributable or deployable to a team where several people want access to the same application. So kind of building out a web app gives you the flexibility of both hosting locally and on a server without having to do any changes to your code. So the app was set up, just a quick kind of overview of the app workflow. We had a database, which was in this case Petrel, where we had a well that we wanted to use as kind of our type well for building this classifier. And in this type well, we had 2 existing lithofacies logs. So we had a manually interpreted log from our geologist. They had a third-party log. So they had a vendor create a log from a lot of data, including, for example, image logs. So that third-party log was a very, very good and very, very detailed lithology log. But for our purpose, it was actually too detailed. We can pick out, or we can build a model that could pick out the same amount of detail just from logs as they'd kind of done with this with the image logs, for example. And then we added a third option, which is to create a kind of pseudo lithofacies log using clustering. So for those who are familiar with machine learning, clustering is basically like an unsupervised machine learning. There are many clustering algorithms. Clustering in itself is unsupervised. So basically, what you do is that you ask, or you have an algorithm try to separate your data out in kind of as distinct groups as the algorithm can create from a data set. So once we had, a lithofacies input, we handle that data, we filter it, we do whatever type of handling of that data that you need, replace missing data, splice logs, remove depth trends if necessary, etc. As our data was coming out of Petrel, they had been kind of QC'd by a petrophysicist, so our data was actually quite good as it was going into this workflow. Once you have a good hold of your data, you then use that data to train a classifier. So then you need to do some testing to see what type of classifier actually works well for my data, and how can I train it, how can I tweak that classifier to work as well as possible with my data. So once you've trained the classifier, you would then use some tools, like, for instance, I mentioned SHAP. That's the library that we used to evaluate the models that we built, to see if it actually performed well, if it performed as expected. And once we kind of iterated through through that process a fair amount of times. So training a classifier, evaluating it, retraining the classifier, going back and forth. We ended up with a classifier that we had a fair amount of confidence in. So from that, you can then use that trained classifier to generate facies logs on unseen data. So basically the new wells that were coming in. So well logs from the new wells that were coming in. And then obviously we're getting down to these two gray blobs here in this workflow. So basically, once you've generated these lithofacies logs, we would then have the geologist look at them, QC them. You know, if there were any anything that kind of stood out as like an unwanted artifact or something's not being separated well, we can then push it back, retrain the classifier, and go on. If you're happy with it, then we would then push it back into the file system, which was Petrel in this specific case. So just a quick overview before I jump into the app itself. So we built kind of like an interface where you could navigate through different panes to perform different parts of this workflow. And it was kind of important that we added a lot of kind of QC steps, so that the user who's used to kind of viewing their data in Petrel, for instance, has the ability to see the data as they're used to seeing it. So we're adding a lot of well log viewers, for instance, that you can see how your logs perform as you progress in your workflow. And then one of the most important points that we wanted to kind of focus on in this kind of app interface was the democratization of the model evaluation. So we're building machine learning models, or we're not building, we're training machine learning models, and we're applying them to data. And there are many ways of evaluating how well that model behaves. But those metrics that we then use to evaluate it aren't necessarily very intuitive to understand or for someone that's not used to machine learning or used to Python or used to the APIs that we were using with scikit-learn, etc. So we spent quite a lot of time with the user to build out QC plots that the geologist found intuitive and easy to understand, so that she could then easily herself look at the output from a classifier and evaluate whether or not this was a classifier that she trusted and wanted to push further into her workflows. So with that, I'll just step out of this and I'll just go to my desktop. Can you still see my screen? Shout if not. So as I said, we built this Streamlit web app, and I'm just going to host it locally now on my computer. So I have just a bash script where I can launch it from my desktop. So what this does is that it starts up basically a Streamlit app in a browser, and then it just points me to a local host site. So this is the app as it's running. I'm sorry. And we have some tabs here, workflow tabs on the left-hand side that we use to kind of push data through this workflow. So I'll just skip straight to create lithology log in the interest of time here. So we can select an input well. So I'll do that first, and then I have some wells on my desktop. So I'll just grab a last file. And you can see as I select an input well, I get some options here. So I can toggle this and see a user guide if I want to. So we try to add these steps kind of throughout the program, so that would be easy for the users to know what's going on, even if they're unfamiliar with, for example, k-means clustering, which we use for this machine learning driven pseudo lithofacies generation. So we'll do that now. We'll basically create a lithofacies log using clustering. Could perhaps be better to use an actual interpreted log as input, but we'll just run through this step just so we can kind of see how easy it would be to create a pseudo lithofacies log. So I can select logs that I would like to then use for my clustering. I'll use just some logs that I know will have a fair amount of impact on my lithology. So I'll just use gamma ray density and neutron porosity. And I'll say I want 3 lithologies. And I could set my minimum and maximum depth there over the interval that I would like to run my clustering. I know that I don't actually have porosity data for a lot of this log, so I'll just leave it at the minimum and maximum depth as well. And then once we run this generate k-means, I'll see that I just generate the k-means for the section where I have data. So this is the output. I've now generated a pseudo lithofacies log by basically just clustering the parts of the logs that are the most distinct. So I have 3 colors here. I asked for 3 clusters, so that's good. So if I look at my my logs here, I can maybe zoom in on this. I can see that this section here should be sand. This section here should generally be something shaly. And then if I look at my k-means clusters, see this is picked up as a shale together with this kind of more high gamma ray section here. I obviously have something here that's a very nice sand, it looks like. High density, low porosity. Maybe it's fluid filled. Let's hope. And then I have some sand up here with slightly more slightly higher gamma ray. So that's interesting. I have 2 sands and 1 shale. So what I can do if I'm happy with this k-means clusters log, I can download it just for future reference if I want it. I can then I'll save that as a last file, and I can load that back into Petrel if I want, or wherever else I want it. I just want to mention here as well, if you remember back to Sebastian's talk earlier, this could easily be hooked up to Python Tool Pro, so you can then just kind of, instead of loading files here, you can then just browse whatever is available to you in a running Petrel project. So once I've created a log, I can go in and I can actually define what my lithologies are here. If I hover over this, I see this is just called cluster 0. This is called cluster 2. So it doesn't really hold any geological meaning. I want to kind of give this meaning. So I know that cluster 0 is shale. Cluster 1 is, yeah, would you say that? Maybe dirty sand, and then sand, and then cluster 2 is cleaner sand. So we can just call it that. So I'll say cluster 0 is shale. Give it a color. I'll say cluster 1 is that was sand, wasn't it? Doesn't really matter. Okay. Slightly more orange. And then this was my clean sand. So I give this a bright yellow. So what I can do now with this definition here, I can save that. And if I want to use then this k-means log to build a classifier, I'll use it together with this definition so that when I apply my classifier to a new well, I can actually say, you know, I'm predicting shale here instead of cluster 0. So I'm basically just giving it geological meaning. So I'll download this geology description. You see it downloaded here, so it's just basically a text file with a dictionary in it. And then I'll move forward to building a classifier from a well. So up here, we used clustering, which was unsupervised. I basically just pushed in this data from these 3 columns, or these 3 logs, and I had the computer then, or the code, return to me 3 distinct groups within these 3 logs. What I want to do now is I want to use that data, but I want to create a relationship between some input data. So I'll just for simplicity, I'll choose the same input data. I could have chosen whatever input data I wanted. It does not need to be the same 3 logs. It could be more logs, it could be fewer logs, whatever. And I want to build a relationship between those logs and this generated k-means log. So instead of just kind of finding the most distinct groups, I want to find the relationships between these 3 logs and this log. I can select, we implement a fair, or we tried quite a lot of different algorithms here, and then we ended up with 3 that we actually implemented. And we'll just leave this at random forest classifier. It's a classifier that works well with spatial data, and it's kind of it doesn't necessarily perform as well as a neural net if you have large amounts of data for well logs. But for kind of smaller data sets, working with well logs, random forest classifier is actually generally a very well performing algorithm. I'll leave minimum and maximum depth as it is, and then I'll just hit train classifier, and then we can talk a bit more about this test train split as that runs. So right now I hit train classifier, and I'm now training it random forest classifier from these feature logs, gamma ray, density, porosity, and then kind of trying to build relationships between those input logs and this lithology log here. So to kind of validate how well this random forest classifier works, I've said that I want to hold back a random sample of 20% of my data. So that I use the remaining 80% I used to build this relationship. I used it to train my random forest classifier to find a relationship between input logs and this lithology log that I want to then kind of be able to predict. And then I'm going to use that 20% that I kind of put to the side and didn't train or used to train my random forest classifier to validate the performance of my classifier once it has been trained. So by doing that, I can then say something, or I can quantify basically how well my classifier actually performs. And there it ran. It's a very useful progression bar here. So it's now run. I have a trained classifier. Now I would like to evaluate how my classifier performed. So I have a lot of explanation here. I will kind of skip through because I'll walk you through it down here instead. So the first output that we use to kind of look at the performance of this classifier is just a set of standard classifier scores. So we have basically an accuracy score from the training score, training data set, test data set. Then we have a log loss measure here. So when we're looking at accuracy, which these 2 measures are, it's basically the percentage of times I was right versus the percentage of times I was wrong. Easily put. We have a bit more, it's a bit more complicated. You do a bit of like true positives over false negatives, etc. But in general, it's basically how often am I right? Log loss is basically just a measure you want to have it fairly low. You want your accuracy to be fairly high. So what you're looking for here in these classifier scores, as a kind of layman, is that the word in English? You want a low log loss and you want a high training score and test score. And then at the same time, you want these 2 scores to be fairly similar. So when I'm saying that I have a train score and a test score, for my training score, I'm basically looking at my accuracy for my full training data set. And when I'm looking at my test score, I'm looking at the kind of accuracy for my test data set. So this is the data where I build my data or build my classifier from, and then I just push the data through again, see if I predict the same thing. And this is where I use kind of blind data. And if these 2 differ a lot, say this is very high and this is not so high, then I've overtrained my classifier. If these 2 are fairly similar, and both high, then I've done a good job. I'm running out of time, so I'll just speed up a little bit. Then we build a confusion matrix. So basically lithology versus lithology. And you can see how often you predict, say, clean sand against clean sand. And you can see how often you confuse clean sand with other lithologies. So then, say you very often confuse clean sand and shale, that's probably not a good classifier. So then you'd want to go back and redo kind of your data inputs. Same for feature importance. I have my lithologies here on the side, and I have my feature inputs, so my logs here. And then with a bit of geological knowledge, I can see, okay, clean sand is mainly driven, or at least gamma ray is the biggest driver. Sand density is the biggest driver. It's probably because the gamma ray is fairly similar, and then density is kind of what separates these two. And then you can also see for shale, gamma ray is a big driver. So that's kind of stuff that I would expect with geological or with a geological background when I'm asking for a relationship between these logs and these specific lithologies. So I'll download my trained model, and then I can quickly jump to applying this classifier to a well. So I need to select another input well, and I'll select one that's fairly close to the one that I had. I'll select my pickled classifier, which is in my downloads, so just the last one I had. And then I'll select this lithology description that we created, where I defined or gave a cluster number, basically a lithology name and a color. So I'll pop this in, and then I'll just view my new log to see that it looks fairly okay. So here's my log. It's a bit shorter, but I have I have some shale, I have some sands. Hopefully it will look okay. Then I scroll down, and I can see that the classifier that I loaded was built from gamma ray, density, neutron porosity. If I have name matches between logs in the well that I built the classifier from and the well that I want to apply it to, it will pick out the correct logs automatically. If not, I would just have to go in and select them. So then, once I know that I have the correct logs selected, I can continue to apply classifier. I'll just leave it for the entire section, and then I'll run classifier. This takes a lot less time than training the classifier, just applying it to a new well. And then you can see that I have an output here. So I can see that I'm picking out my shale. I'm picking out some sand here, very low gamma content, and then some higher gamma content sand here. So it actually looks like it's performing quite well. And then on the side here, I have some probability curves, which basically tells me a higher color, high probability of classification or of a point in my dataset falling into a specific class. So I can see, like, okay, I'm very confident that it's shale here. If I scroll in here or zoom in here, sorry, I can see I'm actually fairly confident that it's shale here, 40%, but I'm slightly more confident that it's clean sand. And then a part of me thinks it's just sand. So these probability curves here, I can kind of use as input to any type of uncertainty modeling that I'd like to do, or similar. So at least I have like a measure of how certain am I that my classifier, or how certain is my classifier that this is sand, and is there is there another lithology that's fairly as likely. So I can download this as a LAS file, and then I can then easily upload this back into my file system, which would be Petrel. So if we just open this, then yeah, I have a LAS file here. So that's basically it. See if I have a slide left. Yeah, so that's me. Any questions? Throw them up. We have a minute left.
Thank you very much, Hilde.